Section 9.2, Nuclear Equations. Balancing nuclear equations. This is actually much easier than balancing regular equations. There's a method to the madness, and it's actually just simple addition or subtraction. So here we go. In a balanced nuclear equation, particles are emitted from the nucleus, and the mass number and atomic number may change. But the sum of the mass numbers and the sum of the atomic numbers are equal for the reactants and the products. So let's look and see. So the stuff on the left-hand side will be equal to the stuff on the right-hand side. So, for example, the total mass on the left-hand side is 251. You will notice that the total mass on the right-hand side is 247 plus 4, which is 251. The atomic number sum is the same. It is 98 on one side, and on the other 96 plus 2, which is 98. See, we can do that adding. So the guide to balancing nuclear equations. Write the incomplete nuclear equation, determine the missing mass number, determine the missing atomic number, determine the symbol of the new nucleus, and complete the nuclear equation. So here we go. When a radioactive nucleus emits an alpha particle, a new nucleus forms with a mass number that is decreased by 4 and an atomic number that is decreased by 2. So this radioactive nucleus is just out of balance. It needs to release some mass, and in so doing, quite often the heavier ones emit alpha particles. Now let's remember how an alpha particle is written. So, it is written like that, italicized A, or it's also written as 4,2 helium. So let's look and see. As we write it, we have our uranium on the left side, and it's going to decompose into thorium and an alpha particle. So uranium's mass, total mass, is 238. Why? Because it tells us it's the uranium-238. And its atomic number is 92. Why? Because it's uranium. So on the right-hand side, on the product side, you will see that the new nucleus that was formed, we have the alpha particle that was released, so that would be a 2 for the proton number and a mass for the 4. So then we would know that, okay, 2 plus what number is going to be 92? Okay, well that would have to be 90. And so we look up what element 90 is on the periodic table. Oh, that's thorium. All right. Now then, to find which particular isotope of thorium this is, 4 plus what number is 238? Well, 4 plus 234. So, equation for alpha emission. Write an equation for the alpha decay of radon-222. So, let's see. All right, we know that our radon, we look at the periodic table and find out how many protons are in radon. Oh, it's 86 protons. So we're going to write the number 86 here. And this particular isotope of radon has a mass of 222. So we're going to put 222 up here. Now we know it just says that it goes by alpha decay. So that means that one of the elements that is produced is our alpha, I shouldn't say elements, excuse me. One of the particles that is produced is our alpha particle. Why? Because it says alpha decay. So we write that as 4 and 2 for the proton number. So then what plus 2 is 86? Well, I'm hoping that you know that 84 plus 2 is 86. So then you look up the element to see what element is 84. And meanwhile, while we're here on this page, let's do and find that particular isotope of that element, and we know it is 4 plus some number is 222. So 222 minus 4 is 218. So now the only thing we have to do is figure out which element it is. Well, That's determined by the 84. You look up on the periodic table, and what is 84? But it is polonium. So you'll notice we have written the complete nuclear equation. On the left-hand side, the total protons is 86. On the right-hand side, 84 plus 2 is 86. On the left-hand side, the total mass is 222. The total mass is 218 plus 4, which is 222. So let's write an equation representing a beta particle. So beta particle is an electron emitted from the nucleus when a neutron in the nucleus breaks down, increasing the atomic number by 1. So you will notice in our carbon-14, which is the carbon isotope that is used in carbon dating, it is not stable. And when it breaks down, it releases a beta particle. Now notice, remember how we wrote the beta particle? That the mass is 0. And so we did say that, you know, it also had 0 protons, right? Because it's technically called an electron, so it has no protons. And we know electrons are -1 charge. And you go, well, so what does that do? Well, we write it down here so that when we're figuring out what this element is here, so 7 plus -1 does equal 6, which is what's over here. Great. Well, so then we need this item to have a mass of 14. Why? Because 14 plus 0 is 14, and that's what our carbon-14 was. So here's another example. Write an equation for the decay of potassium-42, a beta emitter. So we have our potassium, and we go and look up what the proton number for potassium is, and it's 19. This particular isotope of potassium is 42. So we know it's decomposing. That's code for an arrow. It is decaying. And so then we know that it's a beta emitter. So we write it as E with a 0 over a -1. So we figure out the math. Okay, if we want, we can do the mass number first or the proton number. It doesn't matter, but let's do the mass number first. So we have to have a 42 total mass because we have a total mass of 42 on the left. So what plus 0 is 42? Well, we can figure that one out. That's 42. Now then, we need to figure out the proton number here. Well, some number minus 1 is 19. Okay, well, that's 20. 20 minus 1 is a 19. So then, we got to figure out what in the world is that element that has a proton number of 20. Well, look up on the periodic table, and that is calcium. So when we would write your complete nuclear equation, you will see that everything, the left-hand side balances out with the right-hand side in regards to the mass number and the proton number. So write the nuclear equation for the beta decay of cobalt-60. Okay, see if you can do this. Press pause. Okay, so we have our cobalt. You look up the proton number, it's 27. And so we know that it is beta decay, so it is something plus our 0 over -1. And so what plus 0 is 60? Well, that's 60. What minus 1 is 27? Well, that has to be 28. So then the next question is what is the element with a proton number of 28? And that's nickel. So as you can see, we have the complete nuclear equation. We have a total mass of 60 on both sides, and we have a total proton number of 27 on both sides. Now, here's positron emission. Now, you remember how it was written. It was written as a 0 with a +1 charge. And in positron emission, it is as if a proton is converted to a neutron and this positron. So you'll notice that the mass number of the new nucleus is the same, but the atomic number decreases by 1. So here's our manganese. When it is going to go through positron emission, you will notice that it decays into our chromium-49. Why? Because 24 plus 1 is 25, which is then that's the 25 on the left-hand side, 25 on the right, 25 on the left-hand side, and 25 on the right-hand side. And our mass number stays the same. 49 plus 0 is still 49. Now, gamma radiation, energy is emitted from an unstable nucleus, indicated by the letter M, kind of standing for metastable, following the mass number. The mass number and the atomic number of the new nucleus are the same. So you'll notice that the only difference here is it doesn't have the M after it. It has released the gamma radiation. Remember, gamma radiation, it is the most dangerous of all. It has no proton and it has no mass. So here is another summary of the different types of radiation and what's going to be happening with them. Now, radioactive isotopes are produced when a stable nucleus is converted to a radioactive nucleus by bombarding it with a small particle in a process called transmutation. So we can go ahead and bombard things, with nuclear bombardment, and we can create bigger but usually unstable, i.e. radioactive nucleus. Now notice it mentions that we have a non-radioactive boron 10 is bombarded by our alpha particle. The products are radioactive nitrogen 13 and a neutron. See how they write neutron. So a neutron, N, has no proton number. Why? Because that's a neutron. But it does have a mass of 1. Why? Because the neutrons have a mass. All right, so what radioactive isotope is produced when a neutron bombards technetium-98, releasing an alpha particle? All right, well, we've got to figure out, we have a total on the left-hand side of a mass of 99 and a total proton number of 27. So on the right here, what number plus 2 is 27? Well, that proton number must be a 25. And what number plus 4 is 99? Okay, well, that's 95 for the mass number. So you'll notice that this is what they're doing here. Now then, we had said the proton number was 25, so we look up on the periodic table what element has a proton number 25, and that's our manganese. And you then have now written your complete nuclear equation.